What's up everybody, it's your man MKBHD here, and today we're diving into the world of CPU scheduling algorithms. Now you might be thinking CPU scheduling sounds boring, but trust me, this is some seriously cool stuff that powers every computer and smartphone you use. So what is CPU scheduling? Imagine your CPU as a super fast chef with only one stovetop. There's a line of hungry customers representing processes, all waiting for their orders. CPU scheduling is like the chef deciding who gets to use the stovetop first. A good CPU scheduling algorithm ensures processes get CPU time fairly and efficiently. This means your computer runs smoothly and your apps load quickly. In the next sections, we'll break down popular CPU scheduling algorithms. We'll keep it light and easy to understand. Let's get into it. First up, we have the FCFS algorithm. This one's as straightforward as it gets, just like its name suggests. First come, first served. Think of it like a polite queue at the grocery store. Whoever gets in line first gets to check out first. In the context of CPUs, this means that whichever process requests the CPU first gets to use it first. Once a process gets hold of the CPU, it gets to finish its task, no matter how long it takes. Simple, right? Here's a super basic example in C to illustrate. Hash include int main, int arrival underscore time, equal sign 0, 1, 2, int burst underscore time, equal sign 6, 8, 7, int waiting underscore time 3, equal sign 0, 4, int I equal sign 1, I 3, I plus plus, waiting time I equal sign burst time I 1 plus waiting time I 1, print of processed waiting time, and 4, int I equal sign 0, I 3, I plus plus, print %DTST %DN I plus 1 waiting time I. Return 0. While FCFS is straightforward, it has a major drawback. A long process in FCFS can delay shorter processes, making it inefficient overall. Next up, we have shortest job next, also known as shortest job first. This algorithm is all about efficiency. Instead of going in order of arrival, SJN prioritizes the process with the shortest burst time or the shortest task. Think of it like this. If our chef could see how long each customer's order would take, wouldn't it make sense to serve the quickest orders first? That way, everyone gets their food faster, and the chef can move through the line more efficiently. Now, let's see how SJN works in C hash include int main, int burst underscore time, equal sign 6, 8, 7, 3 int processes, equal sign 1, 2, 3, 4, int n equal sign size of processes 0. For int I equal sign 0, in 1 I plus plus. For int j equal sign 0, jn I 1 j plus plus. If burst time g plus 1, int temp equals sign burst time g equals sign burst time j plus 1, burst time g plus 1 equals sign temp equals sign processes equal sign processes g plus 1, processes at plus 1 equals sign temp, print process at burst time, and for int I equals sign 0, in I plus plus, printf %DDTT %DN processes I burst time e, return 0. SJN is great for minimizing average waiting time, but it has a potential downside. A long process might never get its turn if shorter processes keep arriving. It's a classic case of the rich get richer, or in this case, the short get shorter. Section 4. Priority scheduling. Up next, we have priority scheduling. This one's all about who's got the VIP pass. Each process is assigned a priority level, and the CPU is allocated to the process with the highest priority. Think of it like an emergency room. A patient with a life-threatening condition will always be seen before someone with a common cold, regardless of who arrived first. Let's see a simple C example to demonstrate priority scheduling. C hash include int main, int processes, equal sign 1, 2, 3, 4 int burst underscore time, equal sign 6, 3, 8, 5 int priority, equal sign 2, 1, 4, 3, int n equal sign size of processes 0, for int I equal sign 0, in 1 I plus plus, for int j equal sign 0, jn I 1 j plus plus, if priority j plus 1, int temp equal sign priority j equal sign priority j plus 1, priority j plus 1, equal sign temp equal sign burst time j equal sign burst time g plus 1, burst time j plus 1, equal sign temp equal sign processes j equal sign processes j plus 1, processes j plus 1 equal sign temp, print process priority burst time, for int I equal sign 0, in I plus plus, print %DTT %DN processes I, priority I, burst time I, return 0. priority scheduling is great for making sure important tasks get done quickly. However, it suffers from a problem called starvation. Low-priority processes might keep getting pushed back if high-priority processes keep showing up. Section 5, Round Robin, RRR. Finally, let's talk about Round Robin, RRR, the CPU scheduling equivalent of a game of hot potato. In RRR, each process gets a fixed time slice to use the CPU. Once the time slice is up, the process is moved to the back of the line and the next process gets its turn. Think of it like a group of friends sharing a video game. Each friend gets to play for a set amount of time and then they pass the controller to the next person. This way, everyone gets a chance to play. Round Robin is great for systems where responsiveness is key, like in interactive systems or web servers. It makes sure that no single process can hog the CPU for too long. However, the frequent context switching, swapping between processes, can add some overhead. Section 6, Practical Applications. Now that we've explored some popular CPU scheduling algorithms, let's see where they're used in the real world. Operating systems. Your computer's operating system uses these algorithms and more complex variations to manage which programs get to use the CPU and when. This ensures your computer runs smoothly, even when you have multiple applications open. Web servers. Web servers use algorithms like Round Robin to handle requests from multiple users simultaneously. This ensures that no single user's request monopolizes the server, keeping those websites loading quickly for everyone. Real-time systems. In systems where timing is critical, like in industrial control systems or medical devices, specialized scheduling algorithms are used to ensure that tasks are completed within strict deadlines. Understanding CPU scheduling algorithms gives you a peek behind the curtain of how computers manage their most valuable resource: processing power. Section 7, Conclusion. So there you have it. We've covered the basics of CPU scheduling algorithms, from the simple FCFS to the more dynamic Round Robin. We've seen how these algorithms work, their pros and cons, and where they're used in the real world. Remember, efficient CPU scheduling is crucial for making sure our computers run smoothly and our applications perform well. It's like a well-choreographed dance where the CPU is the dance floor and the processes are the dancers. A good scheduling algorithm ensures that everyone gets their time to shine. Keep in mind that this is just scratching the surface. There are tons of other scheduling algorithms out there, each with its own strengths and weaknesses, but hopefully, this has given you a good foundation to build on. Thanks for tuning in, and I'll catch you in the next one. Peace.